Welcome back, y'all. Let's keep working through example 2 step by step using the LANA algorithm. We are now on to step 3. Step 3 is to create the entire incidence matrix. I'll talk about the adjective entire later on in this video. Let's switch from the quick reference guide to the step-by-step guide. In the step-by-step guide, we're going to see a lot more detail about how to actually complete this step. The first thing that we're going to do is to define an M times N sub G matrix A sub G, which is going to be called the incidence matrix to our directed graph. We're going to use an entry by entry definition for that matrix, which is given here. We'll analyze that in just a second. Notice that in this case, for this example, M, the number of edges, is equal to 12. Another way to say that is the number of circuit elements that we have in our original circuit is 12 because we have 8 resistors, 2 voltage sources, and 2 current sources. N sub G is the number of nodes. That's going to be 7 because we counted the nodes physically. So in this incidence matrix, A sub G, the rows of that matrix are going to correspond to edges. The columns of that matrix are going to correspond to nodes. Again, step 3 is designed to construct the entire incidence matrix A sub G. The number of rows of this matrix corresponds to the number of edges in the digraph model, or the number of elements in our original circuit, rows, edges. The number of columns corresponds to the number of nodes in the digraph model, which is identical to the number of nodes in the original circuit. Because in this circuit we have 12 edges and 7 nodes, we're looking for a 12 by 7 matrix, and we can actually run through the individual elements to find out whether they're equal to 1, -1, or 0, going from row to row, column to column. Let's do that now. The piecewise definition that we see on screen gives us the individual entries of our coefficient matrix as a function of both the row index J and the column index K. Note, linear algebraists, we do not use the row index I because electrical engineers use those for circuits and currents in circuits. J is dedicated for index variables. We will not use I. Don't do it. Don't do it. In order to get started, let's take a look at E1. So in this situation, J would be 1, and then K is the node. E1 goes out of node 1 and into node 7. So we say that node 1, E1 leaves node 1, so that's going to be a 1 there. E1 enters node 7, so that's going to be a -1. Everything else is 0. Let's try another one. We say that edge 2 exits node 2. So in the node 2, edge 2 exits that node, and it enters node 1, and everything else gets 0. Edge 3, let's go ahead and take a look at edge 3. Edge 3 is here. It exits node 2 and enters node 7. So it goes out of node 2 and into node 7. It's worth noting, I like to think about the reason positives and negatives. So imagine the entire system. When something leaves, it contributes to the larger system. And when something enters, it takes away from the larger system. So imagine all these nodes are spewing out money or collecting money. So if I'm spewing out money, I give a positive contribution to the whole system. So I put a positive on the outward. If I'm taking money away, I put a negative because I'm taking money away, right? So from that standpoint, we can actually fill this out. Here is the entire incidence matrix for the directed graph you see on screen associated with that piecewise definition for the entry by entry elements of our incidence matrix. Notice I used what I call an incidence table. So I enumerate the columns of my matrix using the nodes of our circuit or graph, and I enumerate the rows using the edges, and then I can just fill it in accordingly by looking at the actual element there. Notice that because of the way we enumerated our elements, the first 8 elements corresponded to the first 8 resistors. So that's why I kind of put this line over here. That chunk of that matrix is all resistor information. Then the next 2 elements were the 2 voltage sources. Remember, resistor, voltage source, current source. So the next 2 rows were voltage sources, and then the last 2 rows were currents. But that means that the way that we enumerated our edges actually gives a natural partition, block partition, to this matrix. When I transition over to the corresponding entire incidence matrix, literally I just populated each of those elements using that table, I actually get what we call a subblock partitioning. So the entire incidence matrix, remember we said this entire thing was going to be a 12 by 7, and more generally it was going to be the number of edges by the number of nodes, including ground node, because rows were edges, columns were nodes. But then each of these things is going to get, in this case we have 8 resistors and 7 nodes. In this case we have 2 voltage sources and 7 nodes. And in the final case, we have 2 current sources and 7 nodes. And that's what you see here. These subblocks have the exact dimensions that we expect. And in general, the first M sub R, the number of resistors, is going to form a matrix. So M sub R times NG. The second subblock is going to be M sub V times NG, the number of voltage sources times the number of nodes. And then the third subblock is going to be the number of current sources times the number of nodes. And we have fully determined the incidence matrix with respect to the original circuit. The reason that these subscripts show up, this G subscript, is later on in our algorithm, we are going to ground the circuit. So we're going to determine one of the node potentials that we're going to force to be 0. But we're not considering that right now. We are including ground node in these constructions. And the reason that we keep that little sub G on there is because ground is included. The G is included. So the entire incidence matrix encodes all of the edges, all of the nodes, including ground node. When you see the G, it means that ground is included. That's why N sub G is the number of nodes, including ground. When we set the little G to 0, that means that I've forced our ground node to have 0 potential. Do you see it? It's kind of nice notation. Yeah, that took me like 50 hours of thought. Yeah, that's how notation works. So if the G is there, it means ground is included. If the G turns to 0, it means that the ground has been set to 0. Guess what? We just finished step 3. Do you see that matrices arrive from modeling context? Do you see why I hate the word given? Nobody's going to give us a matrix. We got to spend a ton of time getting this. Here in the write-up, you'll see that the dimensions are related back to step 2 of this algorithm. That's why it was so important to define those specifically. In the next video, we're going to go on to step 4, where we define all of the important circuit variables and store that information in vector form. I'll see you in the next video.